Okay, so we're talking about volcanoes and earthquakes, and we'll start with volcanoes. Volcanoes are the result of igneous processes. And when we say igneous processes, we know from our prior discussion or prior review of content that in the rock cycle, there's three major types of rocks. There's the igneous rock, the metamorphic rock, and the sedimentary rock. Sedimentary rock are those rocks that undergo a weathering process. So they break off into sediment. Then if the sediment can find its way into burial and then inevitable lithification and cement together, then you have a sedimentary rock. A metamorphic rock, on the other hand, is a rock where you take an existing rock, you put it under extreme heat and pressure. The rock doesn't melt, but it can change its form in the solid state. A really good example of a metamorphic mineral is a diamond, where in a diamond, you're taking carbon or coal, you're putting it under extreme heat and pressure. You are then changing the mineral in the solid state so it doesn't melt. The bonds are just shifting, and that can create diamond. Then the third type of rock is an igneous rock. And igneous rocks are those rocks that undergo a melt process, and then the resulting recrystallization of the molten material that creates an igneous rock. So when we say volcanoes are the result of igneous processes, what we're essentially alluding to is that we have some type of system where the temperatures are so extreme that rock itself can molt or melt. And then when it melts, and if it rises to the surface, then we have a volcano. That rock at the surface, of course, molten in the form of lava, can then solidify, and that would create an igneous rock, certainly on the surface. And so again, when we talk about volcanoes, it's a result of igneous processes. That means there has to be extreme enough temperature to have a melt. So that stuff can get really high. Now, with that said, our volcanoes derived from igneous processes can be found at hotspots, divergent zones, or convergent zones. And we've chatted about this before when we've taken a look at plate tectonics. And so we know that divergent zones are where two plates are diverging apart. Convergent zones are where plates are converging together. And hotspots are intraplate typically. And that means that the hotspot material is beneath the asthenosphere. It is a stationary hotspot of molten material that can break through the asthenosphere, the lithosphere, and then inevitably get to the crust and have some form of a volcanic activity. A good example of a hotspot, of course, would be Hawaii. Good examples of divergence and convergence. Well, we recall that with convergence, the island of Japan is a nice example, but that's not the only one. If we talk about a place like Mount St. Helens or Mount Rainier, Mount Fuji, of course, on Japan, Mount Vesuvius on Italy, Mount Etna, Mammoth Mountain, as a matter of fact, these are all really good examples of large volcanic activity associated with convergent zones. And I shouldn't forget Mount Pinatubo off the Philippines as well, which was an absolutely huge volcano also. Divergent zones are pretty important as well. A prime example of a volcanic divergent zone would be a place like Iceland. Now, Iceland's a double whammy. It sits right on the Atlantic Rift, but then it's also associated with a hot spot. So it really is a double geological whammy. But we have some volcanic activity over there as well. And then there's various other examples of divergent zones, which of course are going to produce produce volcanic activity. So we'll take a look at those throughout this conversation tonight. Here's a really nice example of a convergent zone. And in fact, this is somewhat apropos to today. There was a very large earthquake right around here off the Juan de Fuca plate in the Northern California region. As a matter of fact, I think it was like 60 to 70 miles off of San Francisco. There is in fact a tsunami warning up here in Northern Cali. And so here we have the Juan de Fuca plate. And the Juan de Fuca plate is relatively small and it's converging with the North American plate. Now, if you're keeping track of us, we're down here in the San Diego region. Here's the San Andreas fault line, and this is a transform boundary. And here we've got the Pacific plate moving northbound relative to the North American plate. But again, we're not finding volcanic activity down here because we're not a convergent zone, we're a transform boundary. When you have a convergent zone and then when you have subduction, one plate subducts beneath the other. And in this process, as you go along this zone here called the Benioff zone, you eventually reach a point where the rock gets so heated that it moltens and it becomes this magma chamber of molten rock and dissolved gases. This molten material can break through the crustal area and then create a volcano. And this is exactly what we see here with the Cascade Mountain Range, which includes Mount St. Helens, for example, Mount Rainier. And we do see this type of activity all around the world. We especially see it along the Pacific Rim, because along the Pacific Rim, you've got the entire rim of the Pacific. We're talking about here, going to Alaska, the Aleutian Islands, for example, all the way down here. We have the Philippines, Japan, all the way down here. Here's the East Pacific Rise, where we have a nice divergent zone. And so all around the Pacific Rim, there is activity, both volcanic and earthquake activity, hence the name Ring of Fire. But again, this is a really nice example. Now, another question is, why is it that the Juan de Fuca plate is the plate subducting beneath the North American plate? Well, the North American plate is a continental plate. And the continental rock has a lot of granitic rock and acidic rock. What that means is continents contain a lot of silicon dioxide or quartzy material. Whereas here, the Juan de Fuca plate is an oceanic plate. And here, the predominant rock is basaltic. And so basaltic rock is iron rich, whereas granitic rock is quartz rich. As it turns out, the basaltic rock is heavier than the granitic rock or the continental rock. So when these plates collide, the heavier oceanic crust is going to get subducted beneath the lighter weight continental crust. And that's why we see the subduction of the oceanic plate going beneath the continental plate. But again, this is a really nice example of a convergent process. So what type of volcanoes do we get? Well, let's take a look. We're going to concentrate on three primary types of volcanoes. Let me see, there's a chat. Got you. There's three primary types of volcanoes. And the first we're going to look at is called the shield volcano. And a shield volcano is broad, slightly domed, as you see here. This is Mauna Loa and Mauna Kea on the Big Island of Hawaii, and we find that right here in my little schematic diagram. It's primarily made of basaltic or fluid lava, and is generally large in size. Now, we know it's going to be basaltic because you find Hawaii in the middle of the Pacific Plate. And in the middle of the Pacific Plate, you're far away from continental rock. Therefore, you don't have a lot of quartzy silicon dioxide material getting blended into the magma. Therefore, it's primarily going to be basaltic and iron rich. Let me put a star by that, because that's actually going to become important later on in our conversation when we ask what makes a volcano very violent versus what makes a volcano a little bit more passive. And iron or lack thereof is going to be the big key. Okay, so this is Big Island, and here's Kilauea. And you've probably seen Kilauea in the news because Kilauea is very active. We're right on top of the hot spot. Here's another type of volcano. This is called a cinder cone. And a cinder cone is built from ejected lava fragments. So you have lava fragments that come out of this volcano. Little pieces, we call those pyroclastic materials or even little volcanic bombs. They're fairly small, these guys. And then they line up all along the base of this volcano, and we call it, therefore, a cinder cone. Now, for those of you who are into Disney fairy tales, you know about Cinderella. Cinderella is named, of course, Cinderella because her evil stepmom made her clean up the fireplace all the time, and she would get cinders all over her, so they called her Cinderella. This type of volcano is not nearly as big as a shield, and it doesn't last nearly as long. A shield volcano can last hundreds of thousands to millions of years, i.e. Hawaii. Cinder cones, however, typically last tens of years, maybe a little bit longer. But what tends to happen is if you've got, let's say, a subduction zone, and here's your magma chamber of molten material, you can have what's called a flood basaltic type material where the magma goes underneath the crust and then it seeps out at a different location. And this can create a cinder cone volcano. It's short-lived, it can grow super fast, and they're not huge, certainly not like a shield volcano or a composite cone that we'll talk about in a second, but they can be fairly violent. They can be small and violent. And here, for example, you would have a much bigger volcano right beneath the magma chamber itself. Okay, so this is our cinder cone. And then finally, we have a composite cone volcano or stratovolcano. They're most adjacent to the Pacific Rim, i.e. Mount St. Helens, Mount Rainier. They're typically associated with these convergence zones where you've got an oceanic plate colliding with a continental plate. And again, this is the picture that you'll be getting with these volcanoes. They are large in size. They are the stuff of movies. They're the big, bad, violent type. These are the kind of volcanoes that can really create devastation. Just to give you an example, in 1991, when Mount Pinatubo erupted in the Philippines, there was so much gas and dust emitted into the atmosphere that global temperatures actually dropped by a fraction of a degree. If we take a look at Hekla, Hekla is in Iceland, and Hekla erupted shortly before the French Revolution. And a lot of historians actually believe that the eruption of Hekla in Iceland instigated the French Revolution because there was so much gas and dust that got strewn into the atmosphere that blew across Europe that Europe saw devastating drought. Crops couldn't grow, sun was blocked out, the soil was disrupted, there was acid rain as well. That created famine, and that famine led to unrest, which many, again, historians believe led to the French Revolution. So again, these volcanoes are no joke. They're called stratovolcanoes because they're interbedded with lavas and pyroclastic material. And I'll define what pyroclastic material is in just a second. But if you were to take a cross section of a composite cone volcano, let's just cut it in half, what are we going to see? We're going to see layers of lava flow. So a very smooth layer of lava. And keep in mind what happens is this molten material comes from the magma chamber, goes up the volcanic neck, and then can seep out in the form of lava. But our composite cones aren't done. If it releases a certain amount of lava, it might not be done, but it might go dormant for a little bit. And when it goes dormant, the lava that's in the volcanic neck is going to solidify. But the pressure still exists within the magma chamber. And because it exists within the magma chamber, it can push up and break the cork of the volcanic neck. And when that happens, all of this stuff comes out in a very explosive fashion. Again, this is called pyroclastic material. So now we're going to have a layer of pyroclastic material that is on top of the older lava, which was smoother. Now we've uncorked the volcanic neck. Lava can now flow up and out, and so we'll have another layer of lava that solidifies, and this process just continues, so on and so forth. And so again, it's interbedded lava with pyroclastic material. That is our composite cone or stratovolcano. Okay? Now, of all these volcanoes, again, the most violent is the composite cone. Probably the longest lived will be maybe a shield. Well, but it depends. Composites can last a long time as well. It just depends on how long that convergent zone is actually going to exist. Here's a nice example. Here's Mount St. Helens. This was Mount St. Helens prior to 1980. So this is pre-1980. This is Mount St. Helens post-1980. So I don't know how old y'all are, but I remember in 1980, Mount St. Helens erupted, And this is what happened. The entire face of the mountain literally blew off. It was crazy. Now, this was an unexpected eruption to a certain degree. So it's relatively simple to monitor a volcano. If there's a lot of rumbling in the magma chamber, you know that you're probably looking at an eruption that's about to occur, right? And there's hours upon hours of lead time by these seismographic folks who are monitoring the movement of the magma chamber. So Mount St. Helens was being monitored in 1980, but it was an unexpected eruption because the seismologists didn't expect it to erupt. But what happened is, remember where Mount St. Helens is located. It's on the Ring of Fire, and there was an earthquake, not unlike the one we saw today, the magnitude 7 quake. And the magnitude 7 earthquake, if that had occurred in 1980, which it sort of did, you had a mass slide. Parts of the face of the mountain slid down because of the earthquake. It exposed the volcanic neck that released the gases, and then boom, you had your major volcanic explosion. So again, unexpected. Compare that to 1991 when Mount Pinatubo erupted. Again, the seismologists were monitoring Mount Pinatubo. They saw the magma chamber get pretty excited. They knew it was going to erupt, and they gave, I don't know how many hours of advance notice, but I think if my recollection is correct, at least 10 to 20 hours of advance notice that yes, Pinatubo is going to erupt, so please evacuate the area. And they did that to varying degrees of success. Right? A nice example again of a composite cone volcano. So what comes out of a volcano? Well, the source location itself is going to dictate it to a certain extent. Gases such as water vapor and carbon dioxide come out of a volcano. Lava such as a Pohoihoi flow or an A'a flow come out of a volcano. Right here, this is Pohoihoi. Pohoihoi is sort of smooth and ropey. It doesn't have a lot of jagged edges associated with it. That would actually be an A'a flow. So here's an A'a flow here, and it looks like rubble that's just flowing down the street. That's a nice example of an A'a flow. Here, the dissolved gases are pretty much gone. Here, any dissolved gases pretty much remain. So it's a nice fluid lava versus this guy, which is not quite fluid at all. And of course, you've got your pyroclastic material, such as volcanic bombs and cinders and ash. Here's a volcanic bomb from Mount Pinatubo that blew from the mountain, bounced here, and landed there. They can be big, the size of trucks even. And of course, here's ash. Ash and dust also associated with it. If you take a look at this picture here and you're wondering if I color enhanced it, the answer is no. These are sulfuric deposits, and this also can come from a volcanic event. So again, lots of really interesting stuff that comes from volcanoes, gases, perhaps some of the more important stuff. And of course, many geologists believe that volcanic outgassing led to the water vapor in the atmosphere, then which led to our oceans. And then the carbon dioxide that we see in the atmosphere as well, by and large, originated from these volcanoes as well. So again, our atmosphere and the geology really has a nice connection. All right, so here's some more examples. Here's a nice volcanic bomb. This guy's about 10 centimeters long or so. We also have ash and dust, as I mentioned. We have pumice. So you've probably seen pumice if you've gone to like Bed Bath & Beyond or a store like that. You can buy pumice stones and you can rub them on your hands and your feet and get rid of the calluses, and they're absolutely wonderful. Pumice is actually frothy lava. It's like if you go to a jacuzzi and there's all the froth at the top. Lava can be the same with all the mixture. You get a bunch of air in it and it creates a froth. And when that stuff solidifies, that's what pumice stone is. So it's a really lightweight volcanic rock which can actually float. The pili is walnut size, cinders are pea size. Particles larger than the pili are like blocks, hardened lava, and then bombs, of course, ejected as hot lava. And bombs can be relatively small to very, very large. And these are all pyroclastic pieces of material or fire fragments, because that's what pyroclastic actually means. So here's the question of the night, the big question. What makes a volcano violent? What makes a volcano passive? Here's the key. Silicon dioxide, SiO2, and bubble gum. Now, before you say, is there really bubble gum in a volcano? Let me answer that right away and say, no, of course not. There's no bubble gum in a volcano. That's not where we get our gum from. I'm just using this as an analogy. And so let me go backwards in time to when I was in fifth grade. So when I was in fifth grade, on the last day of school, we had a bubble gum blowing contest. And it was great. Now, I could blow bubbles back then. I really, really could. And also keep in mind that the gum of choice was Bubble Yum or Bubblicious. Now, back in the day when I was a kid, Bubblicious and Bubble Yum came in a pack of 5 pieces. 1, 2, 3, 4, 5. And these pieces were absolutely huge, square pieces of gum. So, I got my Bubble Yum in my mouth. I'm chewing. I go through the round robin of fifth grade. I make it all the way to the finals in the bubblegum blowing contest, and it's between me and another student who I will not name the name in case this person ever watches this video. But I'll just say this. I went first. And so here's me. I'll try to draw me as best as I can. There we go. Got my hair, my eye. And I blow my bubble, and it's a nice bubble. I thought that this was a winner. The bubble popped. It went on my face. I took the gum out of my mouth. I did this to get the gum off my face. Success. I knew I could do it. The next student went up. And here she is. Beautiful long hair. She blows this bubble, and it's probably the biggest bubble I've ever seen. I will say for the record that she cheated, because unlike me, who had 1 piece of gum in my mouth, this person was able to put 3 pieces at least in her mouth, which was not an easy feat because these pieces of gum were absolutely huge. So the only saving grace was when the bubble popped, it went into this student's hair. I saw this student the next day at the bowling alley with the hair cut. Because the gum got all in the hair. All right, why am I telling you this incredible story? Because there's a relationship here. The more gum this student had, the more air or gas that the gum was able to hold. And when the gum popped, it was explosive and it went everywhere. For me, I had 1 piece of gum, not a lot. And I could only hold a certain amount of gum. That was it. And then the gum popped, and it was an explosion, but not super duper explosive, certainly not like this. In our little analogy here, gum and silicon dioxide, that's the relationship. That's the analogy. Silicon dioxide is a long chain molecule. And because it's a long chain molecule, it can hold gases in it. So dissolved gases in magma chamber, it's harder to escape if you've got a lot of silicon dioxide in the magma material. So let's say, for example, we have a magma chamber. So here's our magma chamber. And let's say that this chamber has dissolved gases, because it does. H2O, CH4 with its methane, carbon dioxide, all sorts of gases. These gases are lighter in weight and they're trying to escape up the volcanic neck. If you've got a thin magma that does not have a lot of silicon dioxide, the gases can escape. And if the gases escape, you do not have an explosive buildup. On the other hand, and I'll try to draw this picture a little bit less phallic, my apologies. Here's our magma chamber. And if this magma chamber has a lot of silicon dioxide in the melt, it acts as almost a net. It's a long chain molecule. And gases have an inability to escape rapidly, which means that you get a very explosive buildup of gases. Eventually, the gases will overwhelm the magma chamber, and when it does, that's when you've got the explosion, just like the student with the gum on her face. That is the big explosive volcanic eruption. So again, the key is silicon dioxide. Now, with that in mind, let's go back to our convergent boundary. And here's our subduction zone. Here's our continental plate, and here's our oceanic plate. And you'll recall that the oceanic plate has a lot of basaltic rock on it. That's what the crust is on the oceanic plate. On the other hand, the continental plate has a lot of granitic and andesitic rock. So our granitic rock has a lot of silicon dioxide in it. So now here's our magma chamber. This is our molten material. And as this molten rock goes up through the continental crust, silicon dioxide, which is in the continental crust, gets blended into the mix. Therefore, you have a lot of silicon dioxide in this magma chamber. That leads to the explosive buildup, and that leads to the very explosive composite cone volcanoes. So again, the key here in our discussion is silicon dioxide and the ability of a volcano to hold gases in it, the magma material. If we look at a place like Hawaii, for example, here's our hot spot on Hawaii, and we've got molten material breaking through the basaltic crust, creating the volcanic islands. But again, it's basaltic. It's iron rich. We don't have a whole lot of silicon dioxide. Therefore, the volcanoes here, like these hotspot shield volcanoes, they're not going to be particularly violent, simply because we don't have this same quantity of SiO2. Okay, so that's what makes a violent volcano. That's what makes a passive volcano. Again, the key here is really going to be silicon dioxide. All right, so with that in mind, most volcanoes are located on the margins of the ocean basins, i.e. the Ring of Fire. There's the second group of volcanoes confined to the deep ocean basins, i.e. Hawaii, and those are basaltic in nature. And then the third group includes those found in interiors of continents, like, for example, Yellowstone. And these are in central areas of continents, but keep in mind, these are also going to be hotspot volcanoes. The difference is these are basaltic lavas. These guys that are intercontinental, if they do erupt and they can break through the continent, are going to be more of the composite cone variety. But what tends to happen here is the magma material can get so thick because of the SiO2 that this actually might solidify below ground and not become a volcano at all. And if that's the case, there's going to be an interior igneous process that we'll talk about in just a second. All right, so here are the locations of some of the Earth's major volcanoes. And again, here is the Ring of Fire. And we see along the Ring of Fire that we've got all these volcanoes. Here's the Tonga Islands, which is volcanic in nature, the Galapagos, Paracutin. Paracutin, by the way, is a cinder cone volcano, as is Popocatépetl. That's also cinder cone. Here's Mount St. Helens. Here's Katmai, Valley of 10,000 Smokers, all along the Aleutians here. Here's Mount Fujiyama, which is Mount Fuji. Here's Mount Pinatubo as well. So again, all of these are along the Pacific Rim. Here's Krakatoa. It really is the Ring of Fire. You'll see volcanoes predominantly here. You'll of course see them here, but it's also along the Pacific Rim. Here's Kilimanjaro along the East Pacific Rise, which is a divergence zone. Here's Mount Etna and Mount Vesuvius, both part of convergence. Here's Hekla that I talked about, and Laki and Surtsey. Surtsey, by the way, is an island, a tiny island south of Iceland, but it's associated with that same hotspot and divergence area. And so we see Surtsey, and Surtsey, by the way, formed in the 1960s. It's a really brand new island. And here's Hekla, of course, and again, Hekla is the volcano probably contributing to the French Revolution. So we notice that all these volcanoes are predominantly associated with plate boundaries, and that's of course what we would expect. So a couple major volcanic events that I just wanted to highlight. We've already talked about Mount St. Helens. And we've talked about Mount Pinatubo as well. But here's a really interesting example, Mount Vesuvius. So if I go here, here's Mount Vesuvius in Italy. It's right off the coast of Naples. And this is what Mount Vesuvius looks like. Don't look like much from this picture, but I can guarantee you it is. Mount Vesuvius, excuse me, my apologies. Mount Vesuvius, by the way, is still active. You can take a little bus, go up to here, then hike the rest of the way, see the crater, and then you will actually see an active volcano with active smoke and steam coming from the crater region. So Mount Vesuvius is a convergent zone volcano. It's composite. It erupted last violently in 79 AD. It erupted so fast and with such force that the entire cities of Pompeii and Herculaneum, both adjacent to Mount Vesuvius, were covered in hot ash, not instantaneously, but pretty close to it, meaning that nobody in Pompeii could escape the volcano, so everybody died. There might have been a few people who survived, which were on the bay in a boat, but other than that, everybody else was gone. Now, how do we know this? Well, years and years later, the Italians were excavating the Pompeii area. They were actually planning to build there. And as they dug into the ground, they actually found the old city of Pompeii. And it was completely preserved because it had been overlaid by hot ash. So they start digging it up and they find the old city. It went as so far in various buildings, still had mosaics painted on the buildings. That's how well it would be preserved. Old buildings were found. The very first fast food restaurant probably was found because they found this area. It was a restaurant and it was a bar scene and it was almost like Benihana with 3 pits. And you could go to the pits, of course, and you would cook your food very quickly. And it was like a fast food restaurant. Amazing. But then they also found this. Now, what is this? This, by the way, is a dog. And this dog was chained to a fence. And this dog clearly died in the eruption of Mount Vesuvius in 79 AD. Now, this dog wasn't found like a mummy, but what this dog was buried underneath the hot ash. Of course, most of the tissue had been burned away. Maybe some bones were left over. But by and large, you had this cavity in this hot ash. And so what the archaeologists did was they poured cement into these various cavities. They pulled the casks out, and this is what they found. This is an example of a dog who died in the event. This is an example of the person. He was called the 6-foot man. He was 6 feet, probably someone from Ethiopia, brought over. And this person died this exact way. There are other images of people who died in this event, tragic images. Families, for example, found in basements of building, completely huddled together. People like this with hands over face trying to block themselves from the hot ash. It's an amazing historical snapshot of time. If you go to Pompeii, you can see this. There are glass cases throughout the city of Pompeii that have these examples within them. The 6-foot man is back there as well. And behind the 6-foot man, you can't see it particularly well here, but there's other examples of people. If you go to Herculaneum, which is down the road, there's more of this as well. So again, this is an example of a serious volcano that killed lots of people really fast. And so the power of volcanic activity is really identified in these various historical events. We talked about Hecla, we talked about Vesuvius, Pinatubo, Mount St. Helens. You've seen or heard about movies, Krakatoa, east of Java. I mean, these are big, big deals. They are not small in any sense of the word, and they're extraordinarily tragic. Here is an artist's rendition of the hellfire associated with Mount Vesuvius. There's a recent movie made called Vesuvius where, yeah, everybody died. I'm sorry to spoil it for you, but that's what happened. Everybody died. So Vesuvius, again, is still active, and it'll go off again. When it goes off, I'm not quite sure. Nobody really knows. But when it does, I probably wouldn't want to be in Naples or any of the surrounding area. All right. So That's volcanoes. Very quick look at volcanoes. Now let's take a very quick look at earthquake activity. So another result of tectonic processes are earthquakes, or the quaking of the earth. Earthquakes occur at hotspots, convergent zones, divergent zones, and transform boundaries. The fact of the matter is, wherever there is a plate boundary or some type of hotspot, you will have a quaking of the earth. The earthquake itself is due to a buildup of frictional energy from the movement of the lithospheric plates. So, for example, here's a really nice example of a convergence zone. And here along the Benioff zone, which is where you have the two plates meeting, energy is building up. The fact of the matter is, this isn't in ice. It's not this smooth movement. It doesn't work that way. Rather, it's more like the knuckles. When you got the knuckles together and you got one fist trying to go against the other, there is a frictional buildup, and you can feel it. You can put your hand on the table and try to slide your hand on the table, and you'll feel your skin pulling back. That's all friction. And so this is friction, it's energy, and it builds up. And eventually, the pressure of the plate movement is so severe that the energy is going to be released. It'll pop, it'll snap. And when it does, energy in the form of P waves and S waves are going to be released. We talked about P waves and S waves before when we were trying to figure out what the interior of the Earth looked like, and we'll talk more about these guys in just a second. But these energy waves are going to emanate from the focus, and the focus is the point where the energy is released. Now, if you're wondering what epicenter is simply the point on the surface of the Earth which is right above the focus. So here's the epicenter. Now, if the focus is here, the epicenter would be there. If the focus is down here, then the epicenter would be here, and so on and so forth. So again, the epicenter is just the point above the focus on the surface of the Earth, right? So this is an example of a convergent process, but you can get the same energy buildup along a transform zone, like the San Andreas fault line. You get the same energy buildup with a divergent zone. You get the same energy type of buildup with a movement of a plate and a hot spot below it. Anytime you've got movement of material, you can have frictional energy buildup, and the release of the energy, that's going to be the earthquake. Okay. Now I should, I should put the new picture up. This is silly that I'm not. This is 1999. I mean, if I showed you the new USGS, U.S. Geological Survey image of today of California, you would see the big earthquake that happened off California. In fact, let's do that really quickly. Let's open up a web browser and let's go to usgs.gov. Let's see if this works for us. Here we go. Here's our 7.0 earthquake striking off northern California coast, and we can view the event. And so here it is. We can view this event, and this is where the earthquake occurred. So here's Eureka, California. So right outside of Eureka, about 67 miles or so off the coastline. Now, with that in mind, if I looked at another picture like this one, all these little dots here are indicative of various earthquakes that have occurred along this particular plate boundary. And again, this is the Juan de Fuca plate right here. This is a really interesting area of geological activity. So we see a lot of really cool stuff. Let's go back. I want to try to find a map that's similar to the 1991 map that I'm showing. So let's go to earthquake map of, we'll just say earthquake map. And let's see if this one works for us. Yeah, so here's a nice map. And I can zoom in and we're going to see various earthquakes. And so here is here's all this earthquake activity that occurred within the last 24 hours. That's quite a bit of earthquake activity. And if I press on any of these dots, it'll tell me what the earthquake is. This is a 3.3 magnitude off of Ferndale, California. And again, I can just press these little dots and I'll see it. Now, the point of me showing you this, and let me go back to our lecture notes, and let me play this slide from the current slide. These are seismic net pictures at a period of time. This one was at 4 p.m. Pacific Standard Time in 1999. Let's go back. And this one is 4 p.m., same exact time, same exact day, 1999 on November the 30th. The only difference is this is Southern California, so here's LA, and this is Northern California, here's San Francisco and Berkeley. All of these little squares are representing an earthquake that occurred during the last hour, last day, or last week from November 30th, 1999. And the size of the squares indicating the magnitude from very small to very large. You'll note here that there's a lot of little earthquakes, certainly south of Clear Lake. And on this day, there was an earthquake, a pretty decent sized one right outside of LA, which looks to be around the magnitude 4 that occurred during the last day. Why am I showing you this? I'm showing you this so you can see all the little dots. All the little dots indicating that the Earth is constantly moving. It's plate tectonics. And if you have plate tectonics and if you have buildup of energy from friction, you will have a continual release, and that's exactly what we see. So earthquakes are an absolute normal occurrence, especially for people that live close to tectonic boundaries. Now, will you feel a 4 or a 3 or a 2 or a 1 on the Richter scale? And the answer is probably not. Unless you're super sensitive, you're probably not going to feel a 2 or a 1, maybe a 3 or a 4. You most likely will feel a 5 or a 6 or a 7. But again, there's a lot of these little quakes occurring all the time. Most all of them you're not even going to notice. It's the big ones, of course, that maybe you'll notice, and that'll give you a scare. If that magnitude 7 had occurred right here in Berkeley, the news stories today would be a little bit different, right? Because you're probably going to have a lot more destruction and damage than anything else. If a 7 occurred on the Anatolia plate off of Turkey, you're going to have a lot of destruction, I'm sure. Maybe a lot of people dying as well. So again, it just depends on where these things occur and what the damage can be based upon various infrastructure, which we'll talk about also in a second. All right, so I mentioned P waves and S waves. The energy coming from these earthquakes from the focus are going to be primary waves, which are P waves, and S waves, which are secondary waves. P waves are pushing and pulling like this. And so the damage you would see, the hypothetical damage, might look something like this that you see on this street example. P waves are pull-push. They travel through solids, through liquids, through gases. They have the greatest velocity of all earthquake waves. As a matter of fact, P waves are about 1.7 times faster than S waves, so they move quite quickly. Again, as opposed to the P wave, you have your S wave, which is known as your secondary wave. It's shaky, almost sinusoidal. This is the type of damage that you would see, almost like surfing waves. There's a lot of shaky motion. As we know from our previous discussion, S waves travel only through liquids and not solids. And again, they're about 1.7 times slower than P waves. All right, why am I telling you this? The speed of the P wave versus the S wave is going to be super important when we try to figure out where the epicenters are located. Like, for example, how do we know that this earthquake today occurred 60 some odd miles off the coast of California? How do we know that that's the location of the epicenter? Because I'm going to tell you right now, we know. And we know within centimeters of accuracy that that's where the epicenter is. And we also know the depth of the focus. We know if it's shallow, deep, or medium. We know how deep that thing is as well. And we know it because we can monitor P waves and S waves. So let's get to that. So we determine the strength of an earthquake by using a seismograph and the Richter scale. And the Richter scale was developed in 1935 by Charles Richter, and we'll talk about that in a second. We can determine the location of an earthquake epicenter by following the P waves, the S waves, and doing something called triangulation. All right, so you ready for this? Let's talk first about the Richter scale. So here's the Richter scale. The Richter scale is based upon movement inside of a seismographic machine or a seismographic station. This isn't coming out well. It's a seismograph. Okay, so what's a seismograph? Let's imagine that we have a box. Here's our box. And let's say that we connect the box to bedrock. Now, this is an important distinction. Bedrock is the solid earth. It's like connected to the lithosphere. So when the lithosphere moves, the bedrock moves right with it, as opposed to something like soil. If you've got soil, yes, the soil is moving with the lithosphere, but it can also shake and vibrate because it's not super solid. The key is getting to the core. Let's get to bedrock. And if you can attach yourself to bedrock, when the bedrock moves, it's moving right with the lithosphere. So we know exactly how much the lithosphere is moving due to an earthquake. Okay, so here's the box. And again, we bolt the box to the bedrock. That's what these bolts here are representing. And inside of this box, we're going to have a conveyor belt of paper. And so here's the side view. Here's our paper, and it's moving from a roll, and it's going to the next roll. And so here's our conveyor belt of paper. So this is all paper right here. And then dangling down from the top of the box is a pen. And this pen is attached to a weight. And the design of the weight is to hold the pen straight down. So again, here's our picture, and here's the pen. And it's right on top of this paper. All right. And again, the pen is weighted down. Now let's say that there's an earthquake, and the earth moves this way, or the earth moves this way. This box is moving with the moving earth. And the pen, which is in the top of the box, weighted down, the top is going to move, right? Because the top is moving with the box. The bottom, which is weighted down, is going to be doing this action. And so you see the pen is going to draw a very large line depending upon how much shaking occurs. The paper conveyor belt beneath it is going to move. And therefore, this is going to be the result. If there's a lot of shaking, you're going to get this action. If there's a little shaking, you're going to get this action. That is how the seismograph works. And what Charles Richter did was he came up with a logarithmic scale. And he said, okay, if the amplitude is this big, that's like a 6 on the Richter scale. If the magnitude is this big, that's like a 7 on the Richter scale. And then he equated the number with energy release. So for example, a 3 on the Richter scale is tantamount to about 30 tons of TNT energy release. Every 1 magnitude increase is a 30-fold energy increase. That means a magnitude 4 is 30 times 30 equals 900 tons of TNT energy release. A magnitude 5 is 30 times 30 times 30 equals 27,000 tons of TNT energy release, and so on and so forth. So if our numbers are correct, if you get to a 7, you can do the math. And that's what occurred today. So this is the Richter scale, and again, it was developed in 1935 by Charles Richter. Now you might ask yourself, well, what did they do prior to 1935? And prior to 1935, they used a scale called the Mercalli intensity scale. And the Mercalli intensity scale is, as the name implies, it was developed by Mercalli, and it's an intensity scale. So a 10 on the Mercalli scale would literally mean that the world is shaking a lot and stuff is rolling. A Mercalli 12 might mean stuff is moving, desks are flying, people are getting scared, maybe somebody is screaming. And I kid you not, the Mercalli intensity scale is going to list the type of intensity, excuse me, that someone might go through based upon the shaking of the world. Mercalli is not particularly good in the sense that people react differently to earthquake activity. Some people are more calm, some people get a little bit more scared. So on average, Mercalli works. But if you want to get rid of the quote intensity, then you look at the Richter magnitude scale, which is going to be much more precise and talk about the exact amount that Earth is moving and the energy being released from that activity. Okay, so we've got strength based on Richter. What about location? Okay, so let's look at this first. Again, here is magnitude, and again, we're looking at Richter scale, but I wanted to show you this for a reason. Let's say that you have a seismographic station set up somewhere, and all of a sudden you feel an earthquake. So the first P wave arrives. Then a short time thereafter, the S wave arrives. So here it is. Now remember, P waves travel 1.7 times faster than S waves. So there's an expectation that the P wave will arrive first. But I want you to keep this in mind. Let's say that you are at the epicenter. If you're right at the epicenter, then your P wave and your S wave is going to arrive at your seismographic station at almost the exact same time. So the picture would be this. Here's the first P wave, and then here's the first S wave, right? But now if you're really far away from that epicenter, then the S wave is going to arrive much later than the P wave. Imagine, for example, that you're in a car race, and here's car P and here's car S. And let's just say, for sake of argument, that car P goes 100 miles per hour and car S goes 50 miles per hour. Let's say after 1 hour of driving, we know that car P has gone 100 miles. And after 1 hour of driving, car S has only gone 50 miles. So again, this is the 1 hour mark. After 2 hours, car P has gone 200 miles. But after 2 hours, car S has only gone 100 total miles because it's gone 50 and 50. This has gone 100 and 100. So the total is 200 here. The total is 100 there. After 3 hours, car P has gone yet another 100 miles. So now its total is 300 miles in 3 hours. But car S has only gone another 50 miles. So its total is 150. You see what's happening here? After 1 hour, 50 miles difference. After 2 hours, 100 miles difference. After 3 hours, 150 miles difference. So the longer the difference in time between the arrival of the first P and the first S wave, the further away that earthquake epicenter is. All right. That makes perfect sense, I'm sure. That only gives us, though, distance to an epicenter. It doesn't give us the exact location of the epicenter because we don't know. Let's say that we figure out that the earthquake is like 1,000 miles away from us. We don't know if it's 1,000 miles north or 1,000 miles south or 1,000 miles east or 1,000 miles west. We just know that it's 1,000 miles away. So in order to get the exact location, we have to do something called a triangulation. Now, before we do, I just wanted to show you this really quickly. This is the SP wave curve. And again, P wave and S waves have a 1.7 times differential in speed. So for example, if the first P wave arrives and then 5 minutes later the first S wave arrives, we can use this curve here. And this is a common curve. And that would mean a 5-minute time of differential means that our earthquake epicenter is close to 3,500 kilometers away. If it was 0, we're right on top of the epicenter. If it's 6 minutes, then we know that the earthquake is probably around 4,300 kilometers away, and so on and so forth. So again, this curve is going to give us a really nice difference in time, which is going to give us a difference in distance of epicenter location. But again, this is only good for distance. It doesn't give us exact location. For that, we need to do triangulation. Minimum, you need 3 recording stations. And this is how it works. Let's say, for sake of argument, that we have North America here in our picture. And here's Caltech in Pasadena. They've got a really nice seismographic setup here in Caltech. Let's say that we have down here our friends in Sydney, Australia. They've got a nice setup as well. And let's say we've got another seismographic station set up here in Tokyo. Now, let's say that all these seismographic stations pick up an earthquake that occurs somewhere in the Pacific Ocean. According to the people at Caltech, this earthquake is like 3,000 miles away from them. They don't know where though. So they make a circle with a 3,000-mile radius that goes around Caltech, and they draw the circle. This is not to scale, by the way. They know that the earthquake is somewhere along this circle. Now, to our friends in Tokyo, they also see an earthquake, and this earthquake is around maybe 4,000 miles or so away from them. So they draw a 4,000-mile radius around them. There are 2 places now, here and here, where we've got convergence. We know that the earthquake occurred either here or there. We just don't know which one it is. So we bring in a third party. And the third party is here at Sydney. Or maybe we'll go to Canberra at the Australian National University of Canberra. Either way, doesn't matter. According to them, the earthquake is around 5,000-6,000 miles away. So they draw the radius around them. There's only one place where all 3 circles converge, and it is right here, and it happens to be on Hawaii. So that is where the earthquake occurred. Now, this is triangulation, because we've got 3 locations and we are triangulating it. Truth be told, there are seismographic stations now set up all over the world. There are hundreds upon thousands of seismographic stations. You only need 3 to get the location of an epicenter, but if you want really fine detail, you're going to have a lot more points of data. So now when we say an epicenter is here, and let's say here being Whittier, California, for example, in a building right over there in downtown. It's true. And they're going to know that epicenter location to within centimeters of detail. That's how accurate it can be, because the more seismographic stations you have, the more data you have, the more precise you're going to be. That's how we know of where epicenters are located. Again, by triangulation, and you need to have 3 station recordings at minimum. All right. So that's how we locate it. And if we take a look at where earthquakes are located, once again, we're along the plate boundaries. Here is the Ring of Fire along the Pacific Rim. This is all convergence. This is transform. Here's the East Pacific Rise. Here is also convergence. Here's the Mid-Atlantic Rift. Earthquakes are occurring all along these plate boundaries, very similar to what we see with volcanic activity. Makes perfect sense. Okay, here's a nice case example I always like to look at. Here's Japan. By the way, you had the big earthquake in Kobe. It was like a 6.9 on January 17th, 1995. But these are earthquakes all the way from 1961 to 1994, just as an example. We could update this image a little bit better from 1990s, but it still serves its purpose. From 61 to 94, look at all these earthquakes. The color is representing the depth, the size is representing the magnitude, and these are big earthquakes occurring off Japan. Now you might say, well, why? What is so special about Japan that you would have all this earthquake activity? And the answer is, of course, its geologic location. You've got the convergence of the Philippine plate with the Pacific plate, with the Eurasian plate. You've got the convergence of three plates coming together not only to create the islands of Japan, but to create all that earthquake activity as well. So again, if you were to ask someone from Japan who's lived there a minute, like how many earthquakes have you been in that are big, I'm sure they're going to tell you 20, 30, right? Whereas someone from Southern California, we've got the San Andreas fault line. So you would expect a lot of earthquakes, but big ones, I've lived here most of my life. I can count maybe two or three. So again, the paradigm of a transform boundary versus the convergence of three plate boundaries together, that makes a world of difference. Now, what can result from these earthquakes? Of course, damage, building collapse, fires and gas leaks, car crashes, heart attacks. That's a real thing because people can panic, which can lead to a heart attack. And then, of course, tsunamis. And if you paid attention to the news today, there was a tsunami watch off of California because of the earthquake that occurred off of California. So, what's a tsunami? Well, when you've got displacement like this, let's say that this is a convergence type of displacement, you're literally going to displace water, almost like stepping into a bathtub and having the water slosh around. So here it's a reverse step. So the P waves and the energy waves are moving because of the displacement of water, and so you get a wave. And the wave is simply the energy moving through the water column toward the coastline. This, by the way, isn't necessarily a physical movement of all this water. It's the movement of the energy wave going through the water. Now, if you're on a boat right above the epicenter, you're not going to notice much of anything because the water is super deep. So you're not moving this, you're not sensing this movement of energy. But as you approach the coastline and the water gets shallower and shallower and shallower, you now begin to feel the energy wave because what happens is the energy wave itself gets built up because the bottom of the wave begins to slow down because of friction from the coastline. You'll notice, by the way, out here, the tsunami speed, which is that energy wave, that seismic sea wave, it's clipping at over 800 kilometers an hour. And as you get closer to the coastline, it's slowing down because of the frictional energy buildup of the shallower water slowing the wave down. And by the time the tsunami actually hits the coastline, it's going maybe 50 kilometers an hour. But that's still fast. That's still fast. That's like 30 miles per hour. And what you get to is a big wall of water because again, the energy wave has been truncated and squished together, and the water gets built up and squished together as well because of the energy wave. And so the tsunami is essentially one large crest of a wave. And all this water gets doused on the coastline, and that can create flooding. And by the way, a precursor to all this water coming in is all this water being pulled out. And typically what happens before a tsunami is if you've got a bay and there's a bunch of boats in the bay is going to get devoured of water. The boats basically are on mud, and then the tsunami wave will come in, fill up the bay again, but it'll be a crashing sensation. So all this water will get back into the coastline and completely flood it out. And it's really quite dangerous. And so tsunami watch is really important. And with that in mind, you would expect that in the middle of the Pacific, there would be a tsunami watch. And if you expected that, you would be absolutely correct. So on Honolulu, there's a big tsunami watch center. And it's these folks' job to monitor seismographic stations around the world, especially around the Pacific Rim, to see what kind of earthquake activity is occurring. And then there's a bunch of buoys all along the Pacific Ocean. And these seismologists can actually monitor whether or not there are tsunamis coming toward Hawaii, which is right in the middle of the Pacific Ocean. And notice how long it takes. If you've got an earthquake off New Guinea, for example, it'll take about 10 hours to reach Honolulu. If you've got one off the Aleutian Islands, 5 hours. If there's some type of activity off of South America, maybe around the Galapagos, for example, 12 hours. So again, these folks on Honolulu, they know exactly whether or not a tsunami is on its way, and they can give advance notice. And as a matter of fact, there are actually alarms on Hawaii that will go off. And when they go off, you're told to go from a lower ground to a higher ground area. And in fact, school kids go through tsunami drills on Hawaii, and they're taught to go to places that are the highest ground at a particular school area, just in case a tsunami is going to hit a particular location. Okay, so that's it. There was a tsunami watch off California today because of that earthquake, which is, of course, apropos to our conversation. All right.